Sure, electric vehicles are quick, but what makes the Tesla Model S Plaid the fastest accelerating mass-produced vehicle ever? The three unique electric motors in the battery pack are the heart of the Plaid Das, while there are other contributing elements as well. It is worthwhile to examine Tesla's electric motor ideas in more detail because they are quite inventive. However, let's make sure that you subscribe to our channel and give this video a huge thumbs up before we get started. Now that you've used a compass, you should be aware that its needle always points north in line with Earth's magnetic field. The strongest force of attraction occurs when you bring a magnet close to the compass. This causes the needle to spin in that direction. You may rotate the needle on the compass by moving the magnet around. An illustration of induced rotation is this. However, a magnet can also produce a powerful push or propulsion. An electric motor rotates by using the force of push and pull, but electromagnets are needed for continuous rotation. Although it is not magnetic, copper is a very conductive material, but when there's an electric current passing through it, it turns into an electromagnet. We now have amazing control over the magnetic field as a result. A permanent magnet has an immutable physical north and south pole, similar to the one on your fridge. However, the magnetic field of an electromagnet tracks the path taken by the electrons as they pass through the conductive substance. While there is a great deal of advanced engineering involved, it is not too hard to understand the fundamentals of Tesla's electric motors. Nikola Tesla's innovation served as the basis for Tesla's induction motor design, which relies heavily on electromagnets to function. We can use magnets to generate rotation by passing electricity through conductive materials, which explains why electric cars like the Tesla Model S Plaid are able to accelerate. The magnet's poles will reverse if you reverse the direction of electrical current. This implies that depending on the kind of juice you give them, electromagnets can swing both ways. Furthermore, turning the magnet to reverse its poles is not necessary. The stator and the rotor are the two main parts of an electric motor. The motor's inner center, or rotor, is what spins, while the stator is the outer ring. While the rotor rotates, the stator remains motionless. In this application, rows of permanent magnets arranged lengthwise encircle an iron core, which serves as the rotor. To keep things simple, we'll assume that the ring is surrounded by 4 rows placed equally apart top, bottom, left, and right. As you circle the ring, the alternate poles in each quarter point north, south, north, south, north, south. The stator is a lengthwise circumscribed tube of electromagnets composed of several coils of copper wire. Every wire coil functions as a separate electromagnet, and by adjusting the amount of energy flowing through each coil, it is possible to switch each one on, off, and refill. There is a permanent magnet inside an electromagnet when the rotor is positioned inside the stator. There is always a natural push and pull when two magnets are placed close to one another. The opposite poles will pull in the opposite direction of each other, while the similar poles will push apart. However, the rotation will come to an end after the first alignment is finished. All that's needed to keep the rotation going is to continuously shift the stator magnet's north and south poles around the outer ring. Once more, you accomplish this by adjusting the direction in which electrons pass through the wire coil. The north pole of the rotor will be drawn in tandem with the stator's rotational movement of its south pole. In addition, as the rotor revolves around the ring, the south pole of the stator will push the south pole of the rotor simultaneously. The rotor will spin due to the constant push and pull force, and it will spin more quickly the faster you shift the magnetic field surrounding the stator. The T emblem used by Tesla represents a cross-section of an electric motor. The pointed T shape is a slice of the rotor, while the top curving line is the stator ring. I hope this explanation was clear and largely correct. It might not be sufficient to make a textbook argument, but it should cover the essential points. As Sandy Munro disassembled the Model S Plaid, he discovered something else about the bearings. The rotor inside the stator can spin smoothly because of the bearings. Those were merely regular ball bearings used in earlier Tesla engines, but Tesla has upgraded to ceramic bearings in the Plaid motor. Compared to steel bearings, ceramic bearings have a few advantages such as reduced friction, increased durability, and temperature operation. Sandy Munro also uncovered an intriguing finding about the wiring within the Plaid motor. The wiring in earlier Tesla motors had to be wound by hand, which is a labor-intensive and slow procedure, but Tesla has moved to a new automated wire winding procedure in the Plaid motor. This innovative procedure makes winding faster and more accurate, which can enhance the motor's efficiency and performance. Sandy Munro finally found out that a new kind of insulating substance is used in Plaid motors. The insulation in earlier Tesla motors was composed of a substance known as Nomex, which is frequently utilized in the aircraft sector. But Tesla has shifted to a novel substance called PEEK polyester ether ketone in the Plaid motor. PEEK is a high-performance plastic that works well in high-temperature applications such as electric motors because of its exceptional chemical and heat resistance. Efficiency in production lines has been Tesla's top priority, according to a recent article. This is demonstrated by the fact that every automobile uses the same basic part and doesn't waste time modifying the boards, printing all of them simply state Model 3. For the Model 3, Tesla even created an inverter that they liked so much they included it into every motor in their lineup. The only modification needed for the Plaid inverter board is an explosive fuse that functions as a little bomb, physically breaking two bus connectors that connect the inverter's electricity to the motor by firing two pushers right out of the fuse. This guarantees that in the event of a catastrophic event involving a Model S Plaid, the motors will instantly shut off. Nevertheless, it's unknown what could blow this fuse. Moreover, a Plaid vehicle has 3 identical motors, which makes it the most productive option for manufacturing. The report's investigator, Sandy, discusses the benefits of having 2 motors at the back. There's more simplicity together with more strength. When one motor powers 2 wheels, there is no need for a differential because each wheel is powered by a single motor. Energy loss due to friction or the gear set is increased when there is something like a differential between the engine and the wheel. Since Tesla lacks a transmission, the sole component standing between the Plaid motors and the rear wheels is a single gearbox with a single predetermined gear ratio. Remarkably, the Plaid motor stator is the exact same part as the Model 3 and Y motors, maximizing production efficiency. But the rotor is notably altered. 6 rows of magnets surround the rotor, which is made of 529 of these stars, which make up the iron core of the rotor made of car-shaped laminate sheets used by Tesla. The magnets are then finished with a second laminated piece that perfectly resembles the Tesla T emblem. These caps are just retained in place by the magnets. They are not connected to the rotor's core. Sandy and his team have never seen a design like this, not even within an electric motor. Tesla claims that the laminated star architecture and floating caps provide a 25% improvement in power and torque capability, which confused the hosts a little. Furthermore, the permanent magnets in the Plaid are far more potent than those in most other electric car motors, including the basic motor from Tesla. Monroe and an unofficial source evaluated the force required to remove a bolt from the rotor magnets of different brands of electric cars in order to test the Plaid motor. They discovered that the Model Y needed 112 newtons of force, the BMW i3 needed 93 newtons, and the Mustang Mach-E only needed 81 newtons. In contrast, the Plaid needed 151 newtons. This suggests that the magnets in the Plaid rotor were more than a third more powerful than those in the Model Y and Model 3, and nearly twice as strong as those in the rotors of the Mustang Mach-E. Even though it's a complex issue, becoming knowledgeable about the Plaid's features and technology can make being an electric car fan more enjoyable. The presenters invited viewers to comment on the video and to point out any inaccurate information. In addition, they requested that viewers subscribe to their weekly newsletter and give the video a huge thumbs up. They concluded by thanking the Patreon backers for their assistance in producing top-notch material. That's essentially it for this video. I appreciate you watching, and please remember to hit the thumbs up on this video. I'll see you at the next one. Furthermore, the permanent magnets in the Plaid are far more potent than those in most other electric car motors, including the basic motor from Tesla. Monroe and an unofficial source evaluated the force required to remove a bolt from the rotor magnets of different brands of electric cars in order to test the Plaid motor. They discovered that the Model Y needed 112 newtons of force, the BMW i3 needed 93 newtons, and the Mustang Mach-E only needed 81 newtons. In contrast, the Plaid needed 151 newtons. This suggests that the magnets in the Plaid rotor are more than a third more powerful than those in the Model Y and Model 3, and nearly twice as strong as those in the rotors of the Mustang Mach-E.